The most common mistake in AI engineering isn't writing bad code, it's picking the wrong chip. Marketing tells you to buy what has the highest flops, which stands for floating point operations per second. Engineering reality dictates that your choice of hardware is not just a performance spec sheet item. It is a hard architectural constraint that determines whether your system can ever run in production. Selecting based on raw speed often leads to systems that are too expensive, too slow for inference latency requirements, or fundamentally incompatible with the software stack you need to build. This video breaks down why the fastest chip is rarely the right tool and how a single hardware decision dictates your entire system design and career trajectory. Imagine a developer who bought the absolute most powerful GPU available on the market. The marketing promised raw speed that would crush any benchmark score they cared about. Yet, when their application went live under real-world load, it didn't just slow down, it crashed repeatedly. Why did faster actually mean broken? The answer lies in what engineers often overlook. Memory bandwidth and latency constraints are not secondary concerns to computational power. They are the foundation upon which a system stands or falls. A chip designed for massive training runs might have incredible throughput, but lack the specific architecture needed for low-latency inference, where milliseconds matter more than total calculations per second. This disconnect between marketing hype and engineering reality is why we see such a stark gap in successful deployments today. Current industry research highlights that optimizing for raw computational throughput ignores critical constraints like energy efficiency required for specific tasks. We are seeing a shift away from generating full pixel-based futures toward methods that trade representational richness against compute costs. As noted in recent surveys on world action models, modern AI design is moving from dreaming up entire scenes to extracting only the necessary control signals. Choosing a chip optimized for one paradigm often fails when deployed for another, where low-latency action is required. If you build your system around hardware that generates full video frames when it should be generating simple movement vectors, your latency budget will explode and your costs will become unsustainable. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The data on this misalignment is staggering. There is a documented disconnect between academic expectations of AI hardware capabilities and industrial reality regarding software testing adoption. While 75% of organizations identify AI-driven testing as pivotal to their future operations, only 16% have actually implemented it in production environments. This gap exists because developers often select tools based on first-order metrics like accuracy or raw speed without considering the second-order effects, the long-term economic and workflow transformations required to make those chips work in a live environment. You might have the most accurate model in the world, but if your hardware choice forces you into an expensive vendor ecosystem that slows down iteration cycles, you will never reach that implementation stage. Standard evaluation methods focus narrowly on technical performance within an isolated stack, ignoring how specific hardware choices impact human interaction and system stability over time. Research indicates that current testing fails to capture the complexity of embedding AI into socio-technical systems, a concept dating back decades regarding human-machine interaction. This leads to deployments where the best chip in a lab setting becomes a bottleneck or failure point in production due to unmet latency, cost, or integration constraints. For example, new paradigms like generative information retrieval show that hardware choices must align with whether an application needs information generation, creating new content, or information synthesis grounding responses in existing data. A chip optimized for one paradigm may be inefficient or incapable of the other, forcing engineers to redesign their entire retrieval pipelines if they choose incorrectly. This brings us to the critical impact on your career trajectory. Your choice of hardware defines what you can build and how quickly you can iterate. If you build a system around an architecture that doesn't scale with your data needs, such as choosing a specialized TPU for a workload requiring heavy custom CUDA kernels, you become locked into specific vendor ecosystems. This limits your ability to move between companies or projects later because the skills you developed are tied to proprietary hardware constraints rather than general engineering principles. You might find yourself unable to switch jobs without retraining on entirely new stacks simply because the previous company's infrastructure was built around a single chip type that didn't fit broader industry standards. Understanding the trade-off between generating only necessary control signals and full video generation helps engineers select chips that balance cost against performance. This prevents building systems where inference costs exceed revenue because the hardware was chosen for training speed rather than deployment efficiency. By recognizing that 84% of organizations are not yet successfully implementing AI in testing, viewers learn to prioritize socio-technical fit over raw specs. This means asking, does this chip support the latency requirements of my specific use case before looking at benchmark scores? If your application requires real-time feedback for robotics or interactive chatbots, you need a substrate that prioritizes low-latency inference over massive training throughput. The field is shifting from dreaming less to generating only the necessary control signals and avoiding full pixel-based rendering, because this approach breaks latency budgets immediately when hardware choices are misaligned. Selecting an AI chip isn't about buying speed, it's about choosing an architectural constraint that dictates your entire system design. The gap between interest in testing and actual implementation proves that the problem is not a lack of desire for better tools, but a mismatch between marketing specs and engineering reality. Current evaluation methods focus on first-order effects like accuracy, but they fail to capture the second-order effects, the long-term workforce impact and economic viability required for sustainable AI deployment. AI progress isn't just about bigger models or faster chips in isolation. It is about matching the right substrate to the specific constraints of your application. If you optimize for flops alone, you will end up with a system that looks great on paper but fails under pressure. Stop optimizing for raw speed and start optimizing for your specific system's latency and cost profile. The difference between a successful deployment and a costly failure often comes down to this single choice of hardware architecture before writing a line of code. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.